and gentlemen, I'd like to introduce Dr. Vishal Garg. Dr. Garg is University Chair Professor at Plaksha University. Previously, he was Professor and Head of Center for IT in Building Science at IIIT Hyderabad. His research interests covers smart energy homes, building energy simulation, and cool roofs. Currently, he is working on research associated with district cooling for thermal comfort in residential sector. Coming from engineering background, he has Ph.D. from the IIT Delhi. Dr. Vishal was founding president of Indian chapter of International Building Performance Simulation Association. He is a fellow of IBPSA and recipient of inaugural Arthur H. Rosenfeld Urban Cooling Achievement Award. Today, we are honored to have Dr. Garg as our guest speaker, and he will talk on district cooling for thermal comfort in residential sector. So without further ado, let's welcome Dr. Garg.
So, we all know that HVAC is one of the major energy consuming part in buildings, and especially we are worried about not just the consumption that's happening now, but the consumption that will happen in the future with the increasing use of AC in our buildings. So let us understand, especially with terms of decarbonizing it, if we want to use renewable, then how does it look like? What is our load pattern and what is the renewable pattern? How the PV generates energy, right? So if you see on the x-axis is the 24 hours, and on the y-axis you see the first y-axis you see the load curve for Delhi. You can see that in the afternoon there is a peak around 2 p.m. and then there is a peak in the night time, and the nighttime peak is also similar to the daytime peak, especially when we are talking about summer months. So here this is the load curve for 17th of June. So you see that it's not the peak in the daytime which is worrying, it's the nighttime which is worrying, because in the daytime the red curve shows the typical generation from a photovoltaic system. So the daytime peak we can address through the photovoltaic, but the nighttime is a problem when we don't have PV. So if we add both these, the generation and the consumption, and then we try to see the curves. These are the famous Doug curves, and this is the Doug curve from California. So on the x-axis is 24 hours day, and on the y-axis is the demand. So you can see the demand going up in the morning and then going up in the evening after compensating for the PV. So in the daytime it is dipping because there is a lot of photovoltaic available, and with the passing of the years, 2019 was higher and 2021 is lower. That means more and more photovoltaic is getting into the grid, and therefore the net requirement in the daytime is reducing. But in the night time, we don't have PV. So what do we do for the nighttime residential air conditioning? We can store the energy that we are generating in the daytime and use it in the night time. But what are the options? So the most common option that people talk about is battery storage. So we can have electrical energy storage, a typical battery. But in case of battery, we are doing a lot of conversions, and the battery is expensive. And then again, there are some environmental concerns with the battery. So when our requirement is related to air conditioning, that means thermal. So why don't we save energy in the thermal form itself? So that is what the thought process is. So if we can save thermal energy, in case of air conditioning, it is cooling. In case of heating, it can be as heat. We can store it in sensible heat format. We can store it in latent heat format, or we can do a thermochemical way. In sensible, we can use solids or liquids. And in latent heat, there has to be a phase change from liquid to solid, or from gas to liquid. So these are different options that are available. Just to give you an idea that why we would like to go for latent heat based storage, because the latent heat is So here we have, say for example, water. The sensible heat for water is much lower as compared to the latent heat for water. So for a lesser space and for lesser volume, we can store much more heat. So here is an example. If you want to store 10 kilowatt hour of thermal energy, and if we store it in water with a 5-degree temperature difference between charging and discharging, then we would need 1.71 meter square of meter cube of space. And the same thing, if we want to put it as ice and we are just looking at the latent heat, then we would need 0.11 meter cube of space, right? So the where I'm trying to lead to is that if we can store energy in the daytime in the form of latent heat of a phase change material, then we can store a lot of energy in lesser volume, and then we can discharge this in the night time. There can be various materials. One is, of course, water for phase change, but we can also have other phase change materials. And the advantage with the other phase change materials is that we can have different point at which we can convert from one phase to another. Water is at 0 degrees centigrade, but other phase change materials can be developed at other temperatures. So what is the issue? Like in residential air conditioning, I cannot do storage at each flat level, right? So each flat has, say for example, a split AC or a window AC or VRV or whatever, but we cannot do storage there. And even if we do, it would need a lot of space and it will not get the benefit of diversity. So let's take an example. Suppose I have a AC of 1 ton and I would like to use it for overnight, and assuming 6 hours the compressor is on, that means we would need to store approximately 21 kilowatt hour of thermal energy. And if we store it in water, that means we will need 3,610 kgs of water. Now, where can I put that much water on each AC unit? And then if I don't use it, then I've charged it in the daytime and I'm not using it in the night time, that's wasted. If we take ice, we might need less, just 230 kgs, but still it is a lot of weight. So what we can do, we can aggregate the demand and have a centralized place where we can have a centralized chiller and centralized storage. So to give you an idea that how much beneficial it can be, we did a case study of a residential complex in Hyderabad, and this complex has 387 flats. And if we do the indoor unit total tonnage, then it was about 3,880, so approximately 4,000 tons, right? So indoor tonnage of the indoor units, the tonnage is 4,000 tons. But when we aggregate this, the peak in the whole year was not even 400 tons. So 90% reduction. So with this, there's a huge benefit we get. The chiller requirement is hardly 350 tons as compared to so you can see how much diversity the system can get. And then the storage also reduces a lot. So if we can see the hourly load profile, we can see for the peak month, this is the thermal kilowatt load at different hours. And obviously we are getting nighttime peak, and then there is also an evening time peak. And if we aggregate this, we know the total energy required for the whole day, and then we can design the storage to match that. So how the system works, it's very simple. In the daytime, when clean energy is available, like from photovoltaics, run the chillers and store the energy in the tank, where we might have a phase change material or not phase change material, depending on the design, and reduce the temperature or freeze the material. And in the night time, we circulate the water, the chill water supply from this tank, and the water is cooled from the heat that it gives to this tank. So like this, then the air conditioning can be provided to all the homes. So the challenge here is that now instead of 400 tons that we saw, those 4,000 tons requirement reduced to 400. But if we have to charge the whole ice in the daytime only, then we have to go more than 400, because now we have to run the chillers only for, say, for example, from 10 o'clock to 4 o'clock when the peak solar radiation is available. So in 6 hours now we have to charge the whole ice and use it in the night time. So the chiller size increases. Also, the efficiency goes down because we are now running the chillers in the daytime when the ambient temperature is higher. And also we are trying to bring down the temperature. If we are using ice as a material, phase change material, then we have to bring it down to sub-zero degree centigrade, and then it reduces the efficiency. So these are the challenges, but there are several benefits of using the central and the district cooling system. We get the benefit of diversity. We have a better refrigerant management. We have reduced refrigerant. We have better space utilization and cost savings, and also improved reliability and redundancy that the system can provide. So there are several good examples of district cooling. One of the ones is in Singapore, which is 70,000 tons of refrigeration, a huge underground district cooling system in Marina Bay. Then there are others in various parts of the world, like this is the one in Qatar. Though for India, this is a relatively new concept of district cooling and cooling as a service, but from technological point of view and even from the business point of view, this has been there for a couple of decades in other parts of the world. I'll just take another couple of minutes to talk about what we are doing as a university. We are setting up a living lab here where we can do all these experiments to understand the residential load, to understand how different phase change materials will behave and how the whole system will work. So we are trying to convert one of our hostels totally on storage-based cooling for the night time, and we have done the load profile based on the current usage. We have estimated how much storage is required, how much photovoltaic is required, what size of the chiller is required to charge all the storage in the daytime and use it in the night time. So we are setting this up as a living lab where we can do behavioral studies, where we can do try out different phase change materials, the performance of different phase change materials. We can develop models to forecast what will be the requirement in the night time, because if we store too much and don't use it, then it's getting wasted. If we store less, then we have to in the night time run chiller on energy which is not clean. So all these things we are trying to set up a lab where we can do these experiments. So I think I'll stop here. Okay, thank you.
Thank you, Dr. Vishal, for taking up this topic and sharing your views about district cooling for thermal comfort in residential sector.